All right, so today I'm going to begin Chapter 5. Chapter 5 is not going to be covered on the midterm. But you will have a quiz in a week, and that quiz will cover Chapter 5, okay? Okay, so Chapter 5 is all about probability. Okay? And probability can be roughly thought of as tells us how likely or unlikely an event is to occur. Okay, and so it also synonyms include chance, likelihood, I don't know, stuff like that. Okay. Okay, and so I guess before we can really get into probability, we'll talk about randomness. Okay. And in this class, our concept of random will be unpredictable, and showing no patterns. Okay. That said, even though things are random, we can still get a sense of understanding. Okay, unpredictable and showing no patterns. So So as far as individual outcomes of random events, the individual outcomes are unpredictable and the individual outcomes show no patterns, but aggregated together, we might be able to understand something. Okay, and so kind of our most basic example will be a coin flip. Okay, so if you flip a coin, no one can perfectly predict the outcome of any single coin flip, okay? So we cannot predict okay? And if we were to flip the coin a bunch of times, we would not see, there would be no discernible pattern in a sequence of coin flips, okay? Okay. However, we do get the sense, or we do understand, that the probability that a coin will land heads is 0.5, or 1/2, okay? But we can still say something, that the probability a coin will land heads is 1/2, or 0.5. Okay. So we can say these things, and let me week 4, Monday. Okay, and so we'll kind of get into the sense of what all of this means, all right? So even though things are random, doesn't mean we can't understand them, okay? So things can be random, but we can still perhaps discern some kind of understanding, okay? Even if we can't predict individual outcomes. All right. As far as probability goes, we will take on, there's a few things we're going to talk about. We have theoretical probabilities, and empirical probabilities. Okay. So, as far as theoretical probabilities go, in our class we take the frequentist approach, or the frequentist view of probability, okay? So in our course, this is in contrast to the Bayesian view. Okay, so in more advanced classes, and if you were to take some computational based statistics, you'll have a Bayesian view. Okay, and so what the frequentist view is. The frequentist view is the long-run relative frequency. So the probability okay, and when we say long run, we're meaning millions, billions, or numbers approaching infinity. Okay, so long run means close to infinity. Okay, which will not be achievable in real life. Okay, but and so the theoretic probabilities, we have a bunch of rules, mathematical rules that we will use to determine theoretic probabilities. Okay. And I would say, and I would argue, most of our covering of probability will focus on these mathematical rules for theoretic probabilities, okay? And so when we say the coin has a probability of 1/2 landing heads, that's an example of a theoretic probability, okay? That's based on kind of our understanding of what a coin looks like and how a coin works. So our example would be, probability that a coin will land heads is equal to 0.5. Okay? So that's a theoretic probability. Okay, on the other hand, empirical probabilities, these are relative frequencies observed from actual experiments or trials, okay? Actual experiments or even simulations. Okay, so an example of an empirical probability was would be, let's say you are an alien. You've never seen a coin before, okay? You don't understand quite, the physics behind a coin flip. If you wanted to know what is the probability that a coin lands heads, we can ask ourselves, what is the probability a coin will land heads? Okay, and the key here is, we have no understanding of how a coin works. Okay, we don't know how coins work, which is kind of a strange thing to say. But what we can do is we could just repeatedly flip the coin. So we repeatedly flip a coin. So let's say we flip it 1,000 times. Okay, and it lands heads 488 times. Okay, so our relative frequency, our empirical probability, is 0.488. Okay, that's what we're going to say. We're going to say our empirical probability is 0.488. Okay, and so if if you have to report back to the alien mothership about coins or something, you can say, well, based on all of these experiments, we think that a coin lands heads with probability close to 0.488. Okay, and that's not the true probability, but based on our experimentation, this is a pretty good estimate. Okay, and so it seems silly to do this example for something like a coin flip, because as far as theoretic probabilities go, a coin flip is rather easy to understand, right? You've got two sides to a coin. We're going to assume both sides are equally likely, and so the probability that it will land heads is 1/2, and the probability that it'll land tails is also 1/2. Okay, but empirical probabilities are very useful if for situations where we don't have math available, okay? And we can build up, maybe we understand some parts of the math, okay, but we don't understand all of the math combined. So, for example, this happens a lot with sports, okay? So I think, I keep making basketball references, but there was, on ESPN they were talking about who would win the 2015-2016 Warriors versus the 95-96 Bulls, right? We can't actually, we don't have mathematical formulas to pit one team against another, okay? But we have some pretty good computer simulations that are based on the mathematical formulas on our certain parts of the understanding, right? And so we've built up these simulations, and what we do is we have the computer play games of basketball against itself, right? And so if you've ever purchased a sports game or you've watched someone play a sports game, you have the computer play, and you can basically set up two computer players and see what happens, okay? And so we can do this with high-powered computers and have computers play games against itself and just see what happens, okay? And basically, we don't have this side. We don't have the theoretic probability to answer the question, but maybe we can have 1,000 games play out or 10,000 games play out on the computer, and maybe one of the teams will win 60% of the time. And then the answer will be this team has a 60%, about a 60% chance of winning, okay? And of course, when it comes to actual game time, it's either the team's going to win or the team's going to lose, okay? But going in, we have kind of these predictions, something like that, okay? So that's how theoretical probabilities work and empirical probabilities go. In higher levels of statistics, I teach a computational statistics class which gets into simulations and trying to answer questions kind of on this empirical side. But as far as an intro class goes, we're just going to learn the basic rules that cover the theoretic probabilities, okay? And things like the coin has two sides that are equally likely, therefore the coin has a probability of landing heads 1/2, okay? We also have something called the law of large numbers. And this is something you see talked about, especially in the concept, when dealing with industries that depend upon chance. So the casino industry and the insurance industry and things like that. The law of large numbers states that empirical probabilities, as we increase the number of trials, the empirical probability should approach the theoretic probability, okay? And so this is how casinos stay in business, okay? Because, sure, if you go to Las Vegas and you play a few games, you might get lucky and you might win a few games and you might come out ahead, okay? But looking at the grand spectrum of all players across all time and, thousands of players every day, overall, the empirical probability will approach the theoretic probability, and the games are all set up in such a way that the casino has a slight edge under the theoretic probabilities. Okay, so we have some kind of simple rules. So simple rules for theoretic probabilities. Okay, so if we have simple outcomes mean all outcomes are equally likely. Okay, the probability of some event A is going to be equal to the number of outcomes in A divided by total number of possible outcomes. Okay, so all outcomes here are equally likely, and so in this case, we would say, probability that coin lands heads. Okay, well, there's two possible outcomes, right? Heads and tails, and both are equally likely, and so when we look at the coin landing heads, only one of these outcomes counts as heads out of a total possible of two possible outcomes. So we have the probability that the coin lands heads is 1/2, okay? And I think that's simple enough. Okay, some additional rules is that probabilities must always be between 0 and 1. Too many E's there. Okay, so if you ever get a probability, 0 and 1 inclusive, I should say. So if you ever get a probability larger than 1 or a probability less than 0, you have done something wrong, okay? Okay, and then we also have something called the complement. Okay, and complement here is spelled with an E, as opposed to compliment, where you're saying something nice to someone, which you should do every day. Compliment somebody. I'm happy to see all of you guys anyway. So, all right. I love teaching at UCLA because all of the students here are excellent. So, so the complement is basically the event. So the complement of some event A is basically the event that A does not happen. Okay. So if A is the coin lands heads, the complement of A, and we can write this as AC, or it could also be just written as not A, would be the coin does not land heads. Okay. And so this encompasses every possible thing that does not include the coin landing heads. So, you know, if you wanted to, so generally we say we simplify the world and we just say, well, if the coin didn't land heads, then it must have landed tails. But does not land heads would actually include the coin lands on its side, the coin, I don't know, gets eaten by a bird while it's flipping, or I don't know, it vanishes. Every possible other outcome is included in not A, okay? So we often simplify things and just say not heads must then mean tails, okay? But and this sure makes things convenient, but you know, if you're engineering some kind of safety mechanism, perhaps you have to include other possible scenarios. Okay. Oh wait, hang on, let me go back. Okay, and then so we say the probability of not A is going to be equal to 1 minus the probability of A. Okay, is that good? All right. So let's, so imagine a deck of cards. Is everyone familiar with a deck of cards? Yeah. Maybe not. Most of you probably are, but let me just pull up deck of cards. We'll get a picture. Can I copy this? Copy image. Okay, so here is a picture of a deck of cards. So you have 4 suits. You have clubs, spades, hearts, and diamonds. Okay, and then you have ace, 2, 3, all the way up through, well, I think you guys can see the, see the numbers, right? Jack, queen, and king. Okay, so this will be your first clicker question. All right, and your answer choices are 1/2, 1/4, 1/13, and 3/13. Okay. All right. We will say, what is the probability a randomly selected card is, oh, this is too easy. Okay, so we'll say the randomly selected card is black. Okay, so this should be very I guess if it wasn't clear, the cards can be, so clubs would count as black, spades would count as black, hearts would count as red, and diamonds would count as red, okay? Okay, do we all have our clicks in, I think? I see 6 people with the wrong answer, but... Okay, well, I'm going to hit stop. Sorry to these 6 people. And I must misclick maybe, I don't know. Okay, so, all right, yes, the answer is A. We have 26 cards out of 52. So 26 out of 52 are black, okay, which is going to be, which will reduce to 1/2, okay? So out of these 26 cards are black, that reduces to 1/2, so the answer there is 1/2. Okay. Okay, so here is, okay, let's, we'll move on, and we'll just make things a little more interesting. So we have and we have or, okay? We have the words and we have the words or. Okay, so as far as the probability for or events, okay, so we'll say or rules, okay? So if we have, let's say we have 2 events A and B. Two events A and B, then the probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B, okay? It's, I guess it's important to note that in statistics, or is always the inclusive and or, okay? Or is, or always means and or. Okay, and what I mean by this is, because in English, we use the same word or to mean different things, okay? And you can ask the same question and the answers will be different. I don't think I've done this example already in class. So if I asked you the question, do you like chocolate or vanilla ice cream? You would then answer me, I like chocolate ice cream, or I like vanilla ice cream or something like that. So if I say, do you like chocolate or vanilla ice cream? That's what you would say. Okay, I could use the exact same words, and if I just change kind of the pauses, and this is like exaggerated, but I could also say, do you like chocolate or vanilla ice cream? Your answer would now be yes or no, okay? And so in statistics, it's always the second case, okay? When we say A or B here, we're meaning, did A or B just happen? And it's not, did A happen or did B happen? It's, did A or B happen? And so that's always the and or here. Is that okay? And so when we ask, what's the probability of A or B happening? That's the probability of A plus the probability of B minus the probability of A and B, okay? All right, and so as far as, you know, so I'll put on, put this deck of cards back up here, okay? And I'm gonna have a new question. Something happened. Okay, so the question here will be, what is the probability that a card is an ace or clubs? Okay, so this is probability of ace or clubs. Okay. And so your answer choices, okay, so so I guess a probability, what is the probability that I guess a randomly selected card? Okay, are we ready for our answer here? Okay, so 3, 2, 1, click, click. Okay, and the answer is C, is indeed C. Okay. Okay, so you know, there are a few ways we can just answer this. Okay, so when we have the full grid of cards, we can just circle all of the cards that are aces or clubs, okay? And we can say, okay, this one counts, these all count. So I've got 13 clubs, and then 14, 15, 16 cards total that count. So we can just count them all, and we will see that we have 16 out of 52, okay? Or we can take the definition we just learned, which was the probability of ace or clubs is going to be the probability of ace plus the probability of clubs minus the probability of ace and clubs. Okay? So as far as aces go, there's 4 out of 52, okay? So probability of ace will be 4 out of 52, plus the probability of clubs is 1 in 4, or 13 out of 52, if we create a common denominator. And then we have to subtract off the ace and the clubs. And there's only one card that's both ace and clubs, and so that's going to be 1 out of 52. So this math will also give us 16 out of 52. Okay. Is that good with everybody? Yeah? Okay. We often draw little Venn diagrams. Okay. So we'll say this is A and this is B, and then so A or B is equal to this shape, okay? And then and we can say this shape is equal, so the probability of A or B is equal to A plus B, but we have to subtract off the overlap. This is A and B. Okay, and so we can create little tables here. Okay, and so let's say we surveyed 200 people. Okay, and then we'll say, I don't know, out of the 200 people, we'll say 90 own a dog, and we will say 70 own a cat, and we'll say 30 own both. Okay. So I've got dog and no dog, cat and no cat. All right, and then so I'm going to ask you a few questions. All right, so okay, so this will be what clicker question. So what probability if we select a person at random, okay, what is the probability this person has, we'll keep it simple, has a cat or dog. Okay, and let me come up with some answer choices here. Okay, so we'll go ahead and fire that up. So I guess what you can do is you can fill in this table. I set up the table hoping it would help you. So then you can start filling in the other spots. Okay, we'll say 10 more seconds to get your clicks in. Okay, 5, 4, 3, 2, 1. Okay, and that is the correct answer, answer choice D. Okay, so again, what is the probability that this person has a cat or a dog? So this is going to be probability of cat or dog, C or D, is equal to the probability, I'm going to just write cat plus the probability of dog minus the probability of cat and dog. Okay, so we have cat would be 70 out of 200 plus dog, which will be 90 out of 200, minus the overlap cat and dog owning both will be 30 over 200. And if you do the math there, you should get 130 out of 200, which is equal to 0.65. So that's answer choice D. Okay, and if we want to fill this in, okay, we say, okay, well these have to add up, all right? And if I stick in a 30 here, then all of these other numbers must also fill out, okay? So how many people have a cat and do not have a dog? $40, right? Okay. And then how many have a dog and no cat? 60. How many have no dog and no cat? 70 here. Okay. So I'm not going to make a question out of this, but I could just as easily, you know, just based on this information. If you build yourself a table, you can answer many other questions. Okay, so remember, all I gave you was I gave this information, and based on this, you can create this table, right? So this is given. And from here, you can make a table. And with the table, we can now answer things like, you know, if I randomly select a person, what is the probability the person has no cat and no dog. Okay, or we could say has a cat and no dog, or has a dog and no cat. Okay. So all of these can be answered, and what is our answer here? Has a cat and has no dog? Yeah, 0.35. Okay, we would say 70 out of 200. Has a cat and no dog. So this would be 40 out of 200. So these are the people with cats and no dogs, 40 out of 200, so 0.2. Has a dog and no cat. 60 out of 200, 0.3. Okay? And so all of these questions can be answered just from simple bits like this, right? so the last thing I'll cover today is this concept of mutually exclusive events. So mutually exclusive, this is like, I don't know. If you're in a dating relationship, this means like you can't see anyone else, right? So similarly, in statistics, what this means is that if A and B are mutually exclusive, what this means is that if A happens, okay, B cannot happen. Okay? Or if B happens, A cannot happen. So one happening makes the other not allowed. Okay? So basically, if one happens, the other is impossible. Okay, and so what this means, essentially symbolically, we'd say the probability of A and B is 0. Okay? And so if we were to draw a Venn diagram, what this means is that over here we have A, and over here we have B, okay? If we're inside A, we cannot at the same time be inside B, okay? So A and B, the probability of A and B happening together is 0, and so if A and B are mutually exclusive, then the probability of A or B is just equal to the probability of A plus the probability of B, okay? So if you contrast this to the original formula for probability of A or B, which was probability of A plus the probability of B minus the probability of the overlap, you see that they're actually the same. It's just that probability of A and B suddenly becomes 0 when they're mutually exclusive. Okay? And so this simplifies to this when they're mutually exclusive. Okay, that's it for today. I'll see you guys on Wednesday.